Hello and welcome back. In this video, I'm going to begin discussing something called geometric optics. And basically, geometric optics describes how the path of light will change when the light either reflects or transmits through a material. And when we study geometric optics, we typically ignore the wave nature of light. So we're not going to be really looking at interference. We're just going to be looking at the path that the light is traveling. And so we usually describe the direction that light is traveling by using an arrow, which is called a ray. And we've actually used this type of stuff before when we talked about the slit experiment. So for example, when we talked about the double slit experiment, we drew kind of a picture like this. And we said there, the light that travels through the top slit takes a path like this, and the light that's traveling through the bottom slit might take a path like this. So what we've actually drawn here is a ray diagram. So we're using these arrows to indicate the path that light is going to travel. And we're going to use this to describe what happens when light is reflected off of the surface of material and what happens when light is transmitted through a material. So the first thing I want to talk about is what happens when light reflects off of something. And in order to describe this, I first need to introduce a convention that we use to describe the direction that light is traveling. So whenever light hits the surface of a material, we describe the direction that that light was traveling using the angle of incidence. And this angle, as I have shown here in this picture, is always measured with respect to the perpendicular of the surface. So this angle right here is my angle of incidence. So notice we're measuring this angle with respect to the direction that's perpendicular to the surface of the material. We don't measure this angle down here. That's the angle between the ray of light and the surface. Basically, what happens when light reflects off of a smooth surface is that the angle that the light reflects off of the surface is equal to the initial angle that the light hit the surface. So we call this angle the angle of incidence. We call the angle that the light is reflected from the angle of reflection. So we would say that the angle of incidence is equal to the angle of reflection. Now, one important thing to understand is that anytime light hits any object, some of that light is going to be reflected off of that object. Now, some of you might be thinking to yourself, well, how can that be? Because if I look at my wall, for example, I don't see my reflection in the wall. And the reason that this happens is that most objects have a very rough surface. So for example, if you were to look at your wall under a microscope, you would see that the surface of your wall has all of these little bumps in it. And so I kind of have like a zoomed in picture of something like that here at the bottom of this slide. And so you can see here I've just drawn these ray diagrams, and I've done my best to try to make sure that these things are obeying the law of reflection. And we can see here that this light is coming in and it's reflecting off in all different directions. And the reason the light reflects off in all different directions is because the surface here is very rough. And it turns out that this is actually very important, because basically what this tells you is that if you take a step back and you look at this object in a sort of macroscopic type of a picture here, what you're going to have is you're going to have light coming in, and then that light is going to reflect off in basically all different directions. So what this means is that every point on an object acts like a point source of light. So for example, here I have this object and I have some light that's coming in and shining on that object, but then that light is going to reflect off in all different directions. So now if I just ignore this beam of light that's coming in and I just look at the light that's being reflected off, this object looks like a point source of light because it's scattering light in all directions. So you can always treat every single point on an object as a point source of light. And that'll be very important when we start talking about the images that are formed by lenses. Now, of course, you know that when you look into a very smooth surface like a mirror, you can see a reflection on the other side. So how does that happen? Well, if we just go ahead and draw the rays that are scattered off of the top of your head. So again, there's this idea that we have this light that's coming in, it'll hit the top of your head, but then your head is a rough surface, so light's going to scatter off in all directions. And here I have shown the rays that are going to scatter off of your head, and they're going to hit this mirror. And I'm showing the law of reflection, so these rays are going to bounce off, and the angle of reflection will equal the angle of incidence. Now what your eyes see are these beams that are reflected off of the mirror. And if we extrapolate all of these beams backwards into the mirror, we can see that it looks like all of these rays actually came from the same point on the opposite side of the mirror. And this is the basic reason behind why an image forms. So the idea is that the only light that you actually see when you look into the mirror is this light that's reflected off of the mirror. And because all of the light that's reflected off of the mirror looks like it came from these point sources on the opposite side of the mirror, you see an image of yourself whenever you look into the mirror. And one other thing that I really should point out about this, whenever we start talking about geometric optics, so when we start talking about things like lenses and we start talking about curved mirrors and things like that, we're always just going to look at these rays that are scattered off of the top of an object. But it's important to keep in mind that these images would form from the rays that are scattered off of any point on the object. So for example here, if we looked at the light that was scattered off of your face, for example, it would form the same type of pattern. So you have these light rays that are scattered off of your face that hit the mirror, you'd extrapolate them back, and they would all extrapolate to that same point on your face on the other side of the mirror. So even though I'm only showing these rays that are scattered off at the top of your head, we could do this exact same thing for any point on the object in front of the mirror. So again, just to kind of illustrate this basic idea, now because the only thing you see are these reflected rays that are reflected off of the surface of the mirror, if you extrapolate these back, they all look like they came from the same point on this image on the other side of the mirror. So while this is what actually happens up here in the top, what this looks like when you look at these rays that are reflected off of the mirror is that it looks like they're all scattering off of this object on the other side of the mirror. So we've discussed what happens when light reflects off of the surface of an object. The other thing I want to talk about in this video is what happens to light when it passes into another medium. So for example, when light passes into glass or water or something that's transparent like that. Now we've already kind of discussed this when we talked about thin films, and a couple of the things that we observed was that the speed of light can change when it moves into another material, and because of this, the wavelength of light can change as well. So just to kind of review this basic idea, we said that the speed of light inside a material is equal to the speed of light in vacuum divided by the index of refraction of the material. And because the speed of a wave is equal to its frequency times its wavelength, we can plug this in to the equation above, and we see that the frequency of light inside an object times the wavelength of light inside that object is going to be equal to speed of light in vacuum, so that's the frequency times wavelength in vacuum, divided by the index of refraction. And because the frequency doesn't change when you move into a material, we can see that the wavelength of light inside a new material is equal to the wavelength of light in vacuum divided by the index of refraction. Another thing that we observed was that when light moves into another material, there is no phase shift. So you can sometimes get these phase shifts when light reflects off of the surface of an object, but you never get a phase shift when light is transmitted into an object. So if you think back at those animated GIFs that I had showed and the video about the thin films, if you remember looking at those pulses, as they moved into the other material, the pulses that continued moving in that same direction, they never flipped upside down. It was only the reflected beams that sometimes got flipped upside down. And because there's no phase shift in the transmitted beam, this means that wherever we had a wave crest in the incident beam, there needs to be a wave crest in the transmitted beam. So what I'm showing here is I'm showing this red line here. This is the ray. This is telling you the direction that the light is traveling. And then these little black lines here are showing you where the wave crests are. So just kind of illustrate this idea. So we have this maximum up here, there'll be a minimum, and then we have this wave crest here again. And then we have another wave crest here again. And as the light moves into this material, what's going to happen is that the direction that the light is traveling in is going to change. And the reason this has to happen is because this point where these wave crests are, and the light that's traveling in the air, has to meet up at the point where there's a wave crest in the water or the glass or whatever material this is. And the reason that those wave crests have to be at the same place is, again, because there was no phase shift in the transmitted beam. So if I had a peak here, I have to have a peak on the other side of the surface. And because the wavelength is shorter, these wave crests have to be more closely spaced inside the transmitted material. And so what we'll see is that the direction that the light is traveling in has to change so that these wave crests can be brought closer together. So how do we relate the angle of incidence to the direction that the light is traveling after it passes through a material? Well, remember that the angle of incidence is always measured with respect to the direction that's perpendicular to the surface of the object. So this right here is my angle of incidence. And notice that the direction that the light is traveling is perpendicular to this wave front right here. Now actually, I haven't talked about why that is, so let me just kind of illustrate this basic idea. So if we have a whole bunch of beams of light that are all traveling in the same direction, and all of these beams of light came from the same point source, it was really, really far away, then all of these waves are going to have a crest at the same point. So for example, here, at this black line right here, we have a wave crest for this wave up here, and then this wave down here, we have a wave crest at the same place as well. So we have these wave crests all along this line right here, and that line is perpendicular to the direction that the light was traveling in. So because this angle right here is a 90-degree angle, this angle is going to be 90 degrees minus my incident angle. And because this dotted line is perpendicular to the surface, this angle over here is going to be equal to my incident angle. Now, an important thing to notice about this is that I now know one of the angles inside this right triangle right here. And this is a right triangle that's formed by the surface of this material, this wave front, and then this right here, this length, is the wavelength of light. It's the distance between one point where I have a crest in the wave and then the next point where I'd have a crest on the wave. So this is the wavelength of my light. So let me go ahead and just highlight that triangle. And because we're looking at a right triangle, we can use either sine, cosine, or tangent to relate this angle to two of the sides in this triangle. Now, what I really want to do is I want to relate the incident angle to the direction that the light is traveling after it moves into this material. So how do I describe the direction the light is traveling inside this material? Well, again, we're going to measure the angle between the direction that the light is traveling and the direction that's perpendicular to the surface of this material. And we call this angle the transmitted angle. So this is my transmitted angle for this ray. Now, because this dotted line is perpendicular to the surface, this angle right here is going to be equal to 90 degrees minus my transmitted angle. And because the three angles inside a triangle have to add up to 180 degrees, this angle over here is going to be equal to my transmitted angle. And so again, I know an angle inside another another right triangle. So now we have these two right triangles, and the really important thing to notice about these two right triangles is that they share the same hypotenuse. So the hypotenuse for this triangle on the top is this side right here, and the hypotenuse for this triangle on the bottom is that same side. So because the hypotenuses for these two triangles are the same, we can relate a trigonometric function for the top triangle and a trigonometric function for the bottom triangle. Now, because I know a way to relate the wavelength of light in air and the wavelength of light inside the material, and because the hypotenuses of these two triangles are the same, I want to come up with some trigonometric function that's going to relate this side, my wavelength, to this hypotenuse. So if I look at this, the wavelength is opposite the angle theta, so sine of the incident angle is going to be equal to the initial wavelength divided by this hypotenuse. Let me just go ahead and label this. So this side right here is just this hypotenuse of these two triangles. Similarly, sine of the transmitted angle is going to be equal to the wavelength of light inside this material divided by this hypotenuse of the triangle. So now what I can do is I can actually relate these true trigonometric functions so that I can relate the angle of incidence to the transmitted angle. So let me go ahead and open up another blank screen here. And let me just write down those two equations that we just found. So we had sine of the angle of incidence is equal to the initial wavelength divided by the hypotenuse of this triangle. And we have that the sine of the transmitted angle is equal to the wavelength of light in the transmitted material divided by the same hypotenuse. And what I really want to do is I want to come up with some way to relate these two functions. And the basic idea behind this is that I can do this by using the formula for the wavelength of light inside a material. Remember that the wavelength of light inside a material is equal to the wavelength of light in air divided by the index of refraction. So now if I plug that formula into these two expressions here, I'm going to have sine of my incident angle is going to be equal to, so now if I plug that equation into this formula here, I have the wavelength of light in air divided by the index of refraction for the initial material times the hypotenuse. Similarly, over here we have sine of my transmitted angle is equal to the wavelength of light in air divided by the index of refraction of the transmitted material times this hypotenuse. And notice that this term right here, let me go ahead and circle this, the wavelength divided by the hypotenuse is the same for both of these two things. So what I'm going to do is I'm going to put those on one side of the equal sign and everything else on the other side of the equal sign, and then I can set these two things equal to each other. So if I if I multiply the index of refraction over to this side of the equation, I have Ni times sine of the angle of incidence is going to be equal to lambda naught divided by the hypotenuse. But I can do the same thing over here, so I can multiply the index of refraction over to this side of the equal sign, and I'm going to have that the index of refraction of the transmitted material is equal to sine of the angle of transmittance. And that's going to be equal to, again, the same thing, lambda naught divided by the hypotenuse. So what I'm left with is that the index of refraction of the initial material times sine of the angle of incidence is equal to the index of refraction of the transmitted material times sine of the transmitted angle. And this is called Snell's law. So basically, Snell's law relates the angle of incidence to the angle of transmittance. Now, one important thing that I should point out about this equation, because of how we measure our angle of incidence and our transmitted angle, these angles are always going to be less than 90 degrees. And what this means is that if you think about sine of x, so here I'm just going to plot sine. So sine goes up like this and then it comes down. So 90 degrees occurs right here. That's when sine reaches its maximum. So between 0 degrees and 90 degrees, sine is always increasing. So what that means is that the bigger your angle, the bigger the value of sine. And this is really important because this means that if I move into a material with a higher index of refraction, so for example, if Nt is greater than Ni, then that means that theta t has to be less than theta I. That way the product of these two things could still be equal to this. So if n is greater, then the angle has to be smaller. So what this means is that whenever you move into a material with a higher index of refraction, the beam is going to bend inwards towards the perpendicular, so that that transmitted angle, the angle between the perpendicular and the direction the beam is traveling, will be smaller. Let's go ahead and look at a couple of examples. The first example says, a beam of light that is initially traveling through air impinges on a piece of glass. The angle of incidence is 63 degrees and the angle of refraction is 47 degrees. Angle of refraction is just another word for the angle of the transmitted beam. The question asks us to find the speed of light inside the glass. So here is the information that was given to us. Because we're traveling through air initially, our initial index of refraction is 1. We're told our initial angle is 47 degrees and the transmitted angle is 63 degrees. And we weren't told the index of refraction of the transmitted material, and we're going to need to calculate that to figure out how fast the light was traveling inside the glass. That's really what we were asked to find. So of course we can find the index of refraction inside the transmitted material by using Snell's law. So Snell's law says the index of refraction in the initial material times sine of the angle of incidence is equal to the index of refraction inside the transmitted material times sine of the transmitted angle. And now if I solve for the index of refraction inside the transmitted material, I can see that this is equal to the index of refraction inside the initial material times sine of the angle of incidence divided by sine of the transmitted angle. And if I plug all my numbers into this, I can see that this is equal to 1.22. Now again, anytime you do these types of calculations where I'm asking you to solve for an index of refraction, you should always step back and ask, does that that answer that you just found makes sense. So in this case, we got 1.22. So yes, this does make sense because it's greater than 1. Remember, the index of a fraction always has to be greater than 1. Now, the speed of light inside a material is equal to the speed of light in vacuum divided by the index of refraction. So if I plug this number into here, so we have 3 times 10 to the 8 meters per second divided by 1.22, and if we plug this into a calculator, we get 2.46 times 10 to the 8 meters per second. So that was how fast light was traveling inside the glass. So let's take a look at another example. This example says a spotlight mounted to a boat is used to look for an object at the bottom of a shallow lake. The spotlight is 2.5 meters above the water, and the light strikes the water a distance 8 meters horizontally from the spotlight. The depth of the water is 4 meters, and the index of refraction of water is 4/3. How far horizontally does the beam travel before striking the floor of the lake? So I have a little picture here illustrating this problem. So the idea is that the beam is going to travel 8 meters before striking the water, and then because the beam is at an angle, it's going to continue traveling a little bit further in this horizontal direction before it strikes the bottom of the lake. And we want to figure out what that total distance is that the beam travels horizontally before reaching the bottom of the lake. So that's this distance d here. And the basic approach that we're going to use to this is that we're going to figure out how far the beam travels horizontally in water, and then we can just simply add 8 meters to that. Now, this is a little bit tricky, and the reason that this is a little bit a more difficult problem is because we haven't been given either the angle of incidence or the transmitted angle. We've only been given some of these distances, this 4.5 meters, 8 meters, and then the 4-meter deep lake. So the way we're going to calculate these angles is by using trigonometry. So let me just go ahead and show the two triangles that we're going to be looking at. So on the top of the water, we have this triangle that describes the incident angle. And then below the water, we have a second triangle that describes the path that the light takes inside the water. And again, what we're interested in finding is this distance right here, which I'm going to call delta x. And once we find delta x, we can simply add 8 meters to that to find this distance d. Now, the first thing that I'd like to point out is that because we have these two lines here are parallel, if this angle is my angle of incidence, then this angle inside this triangle is also my angle of incidence. Now, because Snell's law involves the sine of the angle of incidence and the transmitted angle, I'd like to be able to calculate the sine of this angle using this right triangle that we have here. And remember, sine is opposite over hypotenuse. So one way I could do this is I could calculate the length of this hypotenuse, and then I could use the relationship that sine is equal to opposite over hypotenuse to calculate sine of my incident angle. Alternatively, I can use the fact that I know the length of the opposite side and the adjacent side to find this angle by using arctangent. And then once I know that, I could take that angle and plug it into the sine function. So I'm going to go ahead and find the length of this hypotenuse because I think that's a little bit easier. So this is going to be equal to 8 meters squared plus 2.5 meters squared, square rooted. And if I plug that into a calculator, I'll see that the hypotenuse is 8.38 meters. So this means that sine of my angle of incidence, remember this is opposite over hypotenuse, so this is going to be 8 meters divided by 8.38 meters. And I'm going to need this because remember, Snell's law involves the sine of the angle of incidence. So let me go ahead and just write this down as one of my things that I know. So we know that sine of my angle of incidence is equal to 8 meters divided by 8.38 meters. And what I'm interested in finding is this distance, delta x. So the first thing I need to do is I need to figure out my transmitted angle. Once I know my transmitted angle, I can use this triangle down here to calculate delta x. And to find the transmitted angle, I'm going to use Snell's law. So Snell's law tells me that the index of refraction for my initial material times sine of the angle of incidence is equal to the index of refraction for the transmitted material times sine of the transmitted angle. So I can rearrange this to solve for sine of my transmitted angle. So this will be equal to the index of refraction of the initial material times sine of the angle of incidence divided by the index of refraction for the transmitted material. And really, if we take a look at this triangle here, what I want to do is I want to find the length of this opposite side. And the only thing I really know is the length of this adjacent side. So what I'm going to need to do is I'm going to need to calculate this angle theta t. So to do that, to calculate this angle, I'm going to have to take the arc sine of this side over here. So we're going to have theta t, the transmitted angle, is equal to arc sine of ni sine of my angle of incidence divided by the index of refraction for the transmitted material. And remember, sine of the angle of incidence, let me just write this out. So this is arc sine. My initial material was air, so this has an index of refraction of 1. The sine of the incident angle is equal to 8 meters divided by 8.38 meters. So that's what I have in my numerator. And the transmitted material is water, which has an index of refraction of 4/3. And if you plug this into a calculator, you'll see that this angle is going to be equal to 45.7 degrees. So that's what this angle right here is. So let me go ahead and just label that. So this is 45.7 degrees. And the reason that I really needed this angle, if we look at this triangle now, I know the length of the adjacent side, and I'm trying to find the length of the opposite side. So if we think about what trig function relates the opposite and adjacent sides, that's the tangent of theta. So because I need to calculate the tangent of theta, I really need to know what theta is. So if we look at this triangle here, hopefully you can see that tangent of theta is going to be equal to the distance delta x. So it's opposite over adjacent. So it's this distance delta x divided by the adjacent length, which is 4 meters. So I can use that to solve for delta x. So let me go ahead and write this down. So we have that tangent of my transmitted angle is equal to delta x divided by 4 meters, which means that delta x is equal to 4 meters times tangent of my transmitted angle. And since I know my transmitted angle is equal to 45.7 degrees, I can plug this into a calculator, and I'll see that this distance is equal to 4.1 meters. And since delta x is equal to 4.1 meters, that's the distance the light has traveled after it entered the water, then the total distance it's traveled is equal to the horizontal distance the light travels in air plus the horizontal distance the light travels in water. So that's 8 meters plus this 4.1 meters. So this total distance is equal to 12.1 meters. So that's the total horizontal distance the light travels before it strikes the bottom of this lake. Now, another phenomenon that I want to talk about is something that probably all of you are pretty familiar with. If you've ever looked at an object that's sitting at the bottom of a pool, it always looks like this object is a lot closer to the surface of the pool than it actually is. And the depth that the object appears to be at is called the apparent depth. So how do we calculate the apparent depth of an object? Well, I have shown here a ray diagram showing you the light that's scattered off of an object that's at the bottom of a pool. And as the light reaches the surface of the water, it bends outwards like I have shown here. Now, because the only thing you see are these rays that are leaving the water, if you extrapolate these rays backwards, they appear to have come from this object here, which is actually closer to the surface of the water than the actual object. So again, because the only thing you see are these rays outside the water, you see light that appears to have come from an object closer to the surface. And the question is how do we relate this depth to the actual depth of the object? Well, the first thing I should point out is that once again we have two triangles here. We have this triangle formed by the image of the object, or the apparent location of the object, and then we have the second triangle that's formed by the actual location of the object. And what I should point out about these two triangles is that this distance right here, which I'm going to call r, is going to be the same for these two triangles. So again, we can use this then to relate these two triangles. Now notice that this angle theta 2 is the angle of the light that's transmitted from water into air, and this angle 1 is my incident angle. Notice that this angle 1 is the same angle that forms in this triangle right here, and this transmitted angle is the same angle that forms in this triangle up here. Now, another thing to keep in mind is that Snell's law only allows us to relate the sine of these two angles. So that's the opposite, this length r, over the hypotenuse. Now, the hypotenuse isn't really what I'm interested in. I'm interested in the length of the adjacent side. That's going to tell me the depth of these objects. And there's a little bit of a trick that we can use, and that is when these angles are really, really small, sine of theta is approximately equal to tangent of theta. And that's typically going to be the case because if we think about what's actually going on, so you have your eye up here and it's looking at this. Well, all of the light that's scattered from this object that eventually reaches your eye, all of those angles must be really, really small in order to get into your eye. And basically the reason for this is that the diameter of your eye is much, much smaller than the distance between the object and your eye. So all of these angles have to be really, really small because your angle's just relatively small compared to these distances here. So we can actually use this approximation of sine of theta is approximately equal to tangent of theta. So let's go ahead now and just apply Snell's law. So Snell's law would tell me that n1 times sine of theta 1 has to be equal to n2 times sine of theta 2. Now if I apply this approximation to both sides of the equation, we have n1 times tangent of theta 1 is approximately equal to n2 times tangent of theta 2. And if we look at the tangent of theta 1, well, tangent is opposite, that's this length r, divided by adjacent, that's the actual depth of the object. So here we have n1 times r divided by d, and that's approximately equal to n2, and the tangent of theta 2, again that's opposite, that's the length r, divided by adjacent, that's the apparent depth of the object. So this length r is the same for both of them, so we could cancel that out, and if I solve for the apparent depth of the object, I see that it's equal to the actual depth of the object times the ratio of these two indices of refraction. So this is how you calculate the apparent depth of an object when it's sitting at the bottom of a pool. Now, one of the things I should point out about this example is that because the index of refraction of water is greater than the index of refraction of air, the beam of light is going to bend away from the perpendicular when it travels from the water into air. In fact, anytime light travels from a material with a higher index of refraction into a material with a lower index of refraction, the beam of light is going to bend away from the perpendicular. And what this means is that my angle of transmittance is always going to be greater than my angle of incidence. So if I keep rotating this beam to increase my angle of incidence, eventually my transmitted angle is going to be equal to 90 degrees. And when this occurs, this angle of incidence at which this occurs is called the critical angle. So when light comes in at the critical angle, the transmitted angle is equal to 90 degrees. And when this happens, none of the light is actually transmitted through to the other side of the material. And this phenomenon is called total internal reflection. Now, we can calculate this critical angle fairly easily using Snell's law. Remember that Snell's law tells me that the index of refraction of the initial material times the sine of the angle of incidence is going to be equal to the index of refraction for the transmitted material times sine of the angle that the light is transmitted through the material. Now remember that the critical angle occurs when the transmitted angle is equal to 90 degrees, and sine of 90 degrees is equal to 1. So sine of the transmitted angle is just going to be 1. And in this case, the initial angle is my critical angle. So we have that sine of the critical angle is going to be equal to the index of refraction for the transmitted material divided by the index of refraction for the initial material. So the critical angle is equal to arc sine of the index of refraction for the transmitted material divided by the index of refraction for the initial material. One thing I should point out about this is that you should notice that this will only occur when the index of refraction for the initial material is greater than the index of refraction for the transmitted material. And there are two basic reasons you can think about for why this has to be. The first is that the angle has to be bending away from the perpendicular, right? My transmitted angle has to be greater than my incident angle, otherwise I'm not going to be able to have a transmitted angle that's equal to 90 degrees. So that means right away that the initial material has to have a higher index of refraction than the transmitted material, since the beam is bending away from the perpendicular. Another way we can see this is by looking at this formula right here. Now, because sine of theta is always between -1 and 1, and in particular because theta is between 0 and 90 degrees, sine of theta is always going to be between 0 and 1. And if we look at this ratio over here, if the index of refraction for the transmitted material was greater than the index of refraction for the initial material, then this number over here would be greater than 1. And that's impossible. You can't have sine of any angle equal to something that's greater than 1. So that tells you that the initial material that the light is traveling through has to have an index of refraction that's greater than the index of refraction for the transmitted material. Otherwise, you wouldn't be able to set sine of theta equal to this. So I want to work through one last example. And in this example, there is an object that is 2.2 meters below the surface of the water. So we have this pond here, let's say, and it's 2.2 meters deep. And there's this object that's sitting at the bottom of this pond. And the question is how close horizontally do you have to be before the light is going to be able to escape the pond? So the idea is that there's these rays of light that are scattered off of this object, and for rays that are scattered off at these large angles like this, the light's going to hit the surface of the water and it's going to be reflected back. But for rays that are shallower than this, some of the light will be able to escape, like I have shown here. And so that distance that you have to be closer than is given by this critical angle right here. So when you're at this critical angle, like I have shown here, the light's going to hit the water and then it's going to travel parallel to the surface of the water. So for any angle less than that, some of the light will be able to escape. So the basic idea is that we can use the formula for calculating the critical angle, and then once we know the critical angle, we can use this triangle right here to calculate this distance, r. So the idea is that we know that this length is 2.2 meters, and we're trying to get the length of the triangle that's opposite this critical angle. So we can use tangent of theta to find this distance, r. So how do we find the critical angle? Well, the way I always do this is I just like going back to Snell's law. So we have the index of refraction for the initial material times sine of the incidence angle is equal to the index of refraction for the transmitted material times sine for the transmitted material. And I think this is easier than trying to remember a whole bunch of equations. Just remember the idea that the transmitted angle has to be 90 degrees. So sine of 90 degrees is 1. So we have sine of the critical angle is equal to nt divided by ni. So the critical angle is going to be equal to arc sine of nt divided by ni. And the material the light is being transmitted into is air, which has an index of refraction of 1. The initial material was water. It has an index of refraction of 4/3. So we have arc sine of 1 divided by 4/3. And if you plug this into a calculator, you'll see that that critical angle is equal to 48.6 degrees. So going back, this angle right here is 48.6 degrees. Now again, because we know the length of this that is adjacent to the critical angle, and we're trying to find the length of the triangle that is opposite the critical angle, we're going to use tangent of theta to calculate this distance r. So tangent of the critical angle is going to be equal to, so let's think about that, that's going to be equal to the length of the triangle that's opposite the critical angle, so that's r, divided by the length of the triangle that's adjacent to the critical angle, and that's this 2.2 meters. So this is r divided by 2.2 meters. So r is going to be equal to 2.2 meters times tangent of the critical angle. And if I plug the critical angle into here, and I plug this all into a calculator, I'm going to see that this distance r is equal to 2.5 meters. And so that's how close to this object you have to be horizontally before some of the light starts escaping the water. And at this point, I'm going to end the notes on Snell's law and the law of reflection, and in the next lecture we're going to talk about what happens when light strikes lenses, and we'll talk about how lenses can form images.